Hey guys, welcome back. Okay, in this episode what we're going to do is we're going to start talking about the design of the next system, which is going to be our mapping system, our overhead map. One quick side note before I do that. There is one little thing I want to go back to with regards to the light system, which is we're going to need to do one more optimization that I forgot about. I meant to do this in the last video when we were doing the light testing and optimization and tweaking out, and I completely forgot about it. So we're going to optimize the particle draw calls. Okay. So what does that mean? Let me grab my mouse real quick here if I can get it and find my cursor. If we pull up Unity and let's go ahead and run this. Okay, so it's the typical scene that you guys are used to. So I'm going to go to the window and I'm going to go to the profiler while the scene is running. And it doesn't really matter where we are on the scene. Check out this overhead. This overhead's sitting at about 25% of our total scene. It's running at about anywhere between 1 to 1.5 milliseconds. Now if you look, up here, 1 to 1.5 milliseconds is a huge chunk of this time, and a lot of that's going to our overhead. Now where's the overhead coming from? Overhead is comes from a lot of places, but a big place it comes from is from function calls. So let's take a look at that. Look at this number right here. 1,500 function calls are being performed per frame. This is per frame, guys. And so look at all these function calls being done. Now it's not allocating anything to the garbage collector, and even individually the time is kind of minor. Not kind of minor, but it's really minor. But still, we don't need all those draw calls. Now, why are we getting all those draw calls? Right now we have 16 lights active. However, even though the other lights are not active and their particle systems are not emitting, they're still being called. And so if you look at this number, 1550 is I think it's 310 lights times 5 particles per light, and so that it comes up to 1550. So even though the ones there's none of these are actually active, it's still doing all these function calls. So we need to get rid of that, and that might help our overhead number come down a little bit, hopefully. It may not, given that, you know, if you look at this, the time of milliseconds here is 0 all the way down the board. I imagine it'll bring it down some, but it may not bring it down a lot. But still, we don't want that many calls going off. It's unnecessary, and we can fix that pretty easily. So yeah, we'll do that. That'll be the first thing we do in the next video when we start actually getting into the next section of our project. Okay, so that's kind of the sidebar, right? That's kind of just something I forgot to do in the last video. I meant to, and I just completely, you know, there's so many other things we were doing at the time, I just spaced it. So what we're going to look at, guys, let's see if I can adjust this a little bit, is the mapping system. Now, what do we need? What do we need to do an overhead map? Well, there's a few things we need. First of all, we need a overhead representation of the level, right? And you'll need one of these for each level, obviously. And that's, you know, you can hand draw that. I'll show you an easy way to do it. The way that I've done this kind of in the past. Just fairly easy way to go. What else do we need? We do not want to show the player the entire map all at once. We want them to explore, right? So you have this overhead representation of the level, but you don't want to show it to them. So you need this. You need a map cover. Okay, something to put over the top of the map so it only shows what you want the player to see. And the way we're going to do this is we're going to use an alpha channel for this. So this will simply be a texture, and it'll have 4 channels on that texture. It'll have an alpha, a red, a green, and a blue, right? Now, this set right here, we're going to set to black, which is to say 0, 0, 0, right? This, we're going to set initially to 1. Okay. So if you think about it, guys, you're going to have a texture. And this will be our map. There'll be rooms in here, right? And corridors and whatnot. And this will come down here and like such. Then you're going to have something over the top of that. Okay. And this is going to be black, right? This will be all black. And it's going to sit right over the top of this map. And what we're going to do, we're not going to adjust the color of this map, but as the player uncovers stuff, we're going to adjust the alpha. And what the alpha does is it changes it from black to transparent. So as you go from 1 to 0, you go from black to transparent. So as this is sitting over the top, if you take this pixel or this set of pixels right in here and you make them transparent, you'll be able to see underneath to the map below. And that's how we're going to work this. Okay. The third thing we're going to need is a map camera. This will be an orthographic camera, as opposed to a perspective camera, which is the kind of camera that you're used to. An orthographic camera, there's no perspective correcting. If there are 2 objects in the scene and they're both the same size, and one is close to the camera and one is far away from the camera, in a perspective camera, the one that's further away would be smaller, but in an orthographic camera, they would be the same size on the screen. Okay, that's what that means, kind of in a nutshell. And then we're going to need one more thing. We're going to need 2 game objects. In world. These are going to serve as our markers, as our corner markers. Okay, so what does that mean? So if we look at the world from above, as if we were looking at a map of it, but not really the map, the actual world itself, right? So you've got the world in it. It looks, you know, like this. And you're looking down from above. We need to relate this somehow to this. Now, there's no limits on this, right? This goes this way forever, and it goes this way forever. So there's no way to know where this point on the map and this point on the map are supposed to refer to. So what we're going to do is we're going to stick an object. Let me get this out of the way. We're going to stick a game object right about here, and we're going to stick a game object right about here, and that'll represent those 2 points on the map. That way, anything between can be calculated back onto this map area, okay, relative to these 2 points. Okay, and that'll give us a direct relationship between the map and the world. Okay. Now we don't care about the height, right? We don't care about the y-axis because this is an overhead map, so the y-axis doesn't exist as far as it's concerned. We only care about the x and z locations. Okay, so that's what we need for the camera section. So let's talk about, what did I just say? That's what I need for the map. Okay, I'm getting ahead of myself. Let's talk about the camera setup. And when I talk about, when I say the camera, I mean the map camera. Okay. So somewhere in the world, this is not going to be the main camera. The main camera we've already got. But somewhere in the world, we're going to put a camera. And we're going to do something like this. And there's the thing. And here's the lens. And this is an ortho camera. Okay. So he's going to see like somewhere out in here, right? And this is an ortho camera, so it's straight. It's not like a perspective camera would go out like this, right? But this is an ortho, so everything he sees is straight. That's the way ortho cameras work. Okay. In front of that camera, we're going to put a texture. Okay. And then behind that texture, we're going to put another texture. And you guys should already know where I'm going with this. Something like that. Forgive my drawing. Where this one is the alpha cover. And this one is your map. That's pretty much all there is to it, guys. That's the camera setup. Okay. Pull this down a little bit. So there's going to basically be two camera modes here. We'll need one mode for the mini-map. This is the map that sits on the screen, kind of in the maybe in the lower left-hand corner or the lower right-hand corner, that the player can look at as they're playing the game, right? This is a zoomed-in map. This is fully zoomed in. We could add functions to like allow the player to zoom in that mini-map, and we may do. But a second function is going to be an overview map. And this is the map where this is zoomed out. So this is the map which the player will hit some kind of key, right? And so we'll need some kind of key press such as maybe the M key to change between these modes. Now this is a full screen. This is the full screen map, right? So they hit the M and the map comes up. You guys seen this all the time in games. Now it turns out, guys, that these both use the same camera. We do not need to worry about setting up two different cameras for this, or even two different textures or anything like that. It's all the same thing. Okay, just the only difference is this one is zoomed in a little further. This one shows the entire map. And for this one, we can add functions. We can add zoom functions to it. Okay. So we'll have some sort of key press to change between modes, probably some sort of zoom commands, something like that. Okay, so let's talk a little bit about how this kind of works. We've got a player position, right? Really, guys, especially if we're in third-person mode, really what we want is the camera position. This kind of depends, right? You either want what the user of the game is seeing, or what the avatar on the screen is seeing. If you're in third-person mode, they might be two slightly different things, but really, usually you want the camera mode, or the camera position. Now, if you're in first person, this will be the same thing as the player position. Okay. You have this position, right? You need to convert that and that's a world position. Okay. You need to convert that world position to a position on the map texture. And we can do that very easily via those world nodes. It's actually quite a simple calculation if you think about it. So say you've got a, if we move this up a little bit, say the player is in the world like right there. Well, you can get your relative position from this point to here versus, okay, this is kind of your end point. So you can get a like a percentage across they are from this, and the same thing going up. They're here, and then you can compare that versus the full length. And then given that percentage, you just do the same percentage on the world or the texture map. It's very, very simple, actually. Nothing to it. Okay. For the mini-map, which we want the mini-map to show where the player is, generally speaking, right? You just place the camera over that position. Okay, simple, nothing to it. For the overview map, it doesn't matter, okay, because it just shows the entire map, and then they can zoom into where they want. Okay, so that's basically how the camera system is going to work for our camera map. Let's talk about saving and loading. What do we need to do for saving and loading? Well, this is quite simple, right? If they save the game, the only thing you need to save is the alpha map. You don't need to save the map. The map never changes. You really don't need to save anything about the camera. It's going to be, it's going to automatically go to where the player is anyway. The only thing we need to save is this texture right here. So we will save and load the alpha cover. right? It's pretty self-explanatory. I think that's, you know. So, really, guys, we are nearly done. There's only one step left. Which is to adjust the texels on the alpha cover. Everything else we've covered. I mean, it's really not that difficult a system if you think about it, except for this one bit. This is the tricky bit. So let's talk about how we're going to do this. In order to do this, guys, what we need to start with is the depth buffer. So what is a depth buffer? Okay, for every frame that's drawn to the screen, let's see, how do I describe this? It's a fairly easy concept, but it's hard to describe, kind of. When the engine is rendering in certain modes, and I'll talk about that in a minute, it creates a buffer, okay? This buffer is basically a two-dimensional buffer. It is the same size as your screen. So if, say, you're running in, I don't know, what's a screen resolution mode? 1080 by 768 or whatever it is. Okay, so there's 1080 pixels across, and there's 768 pixels down. So it's got this big array, right? And each point in this array represents one pixel on your screen. So what happens is, as the engine is drawing an object, okay, so suppose there's a crate, right, in your scene. I really screwed that up, but okay, hang on a second. That was terrible. Okay, so you've got this crate in your scene, right? And behind it there's like some kind of wall. Okay, if you're looking at that straight on, this point right here would have a greater value than a point right here, right? Because this crate is in front of the wall. So the depth buffer, if you look at the camera, and this is a top view of the camera, right? So it's a top view. So you're looking at this crate that's here and this wall that's behind, right? So the camera's going to project a point. It's going to say, oh, it stops right there. Okay, so there's this in a perspective camera. There's this kind of, if you're looking at it, there's this kind of pyramid above the volume that defines the area that the camera can see. Okay. This right here is the near clipping plane. This right here is the far clipping plane. You might think you would put the near clipping plane at 0, right up against the camera, because anything in front of the camera should be seen. For mathematical reasons, actually, you can't. You put it close, but you don't want to put it right on top of the camera. So there's a little space, and you guys might have seen this in games, where if you get too close to an object, like you stick the camera right up on the top of the object, it'll actually disappear in front of you. That's because if you try to put this near clipping plane at 0, you'll get a bunch of divide by 0 errors because there's a lot of math that goes on involved in all this kind of stuff, and it really causes problems with shadows and stuff. So they actually set this out just a little tiny bit just to prevent those kind of issues. So anything in front of this clipping plane won't be seen. Anything between the clipping plane and the far clipping plane will be seen. Anything past the far clipping plane will not be seen. So if there's a box back here, you can't see this because it's too far away. I can show you guys this. Actually, let's see if I can run this with my pen. Actually, I don't want to run it. Sorry. Let's see if I can grab the camera. I might need to get my mouse out. Hang on a second, guys. The camera's up here. There it is. Let's see. I need to be able to... Oh yeah, there we go. Okay, yeah, we gotta get the mouse out. I can't control Unity with a tablet pen. Okay, so look at this. I know this thing's in the way, but ignoring that for a minute. What is this? Something to do with the camera, which I just lost. Okay, look at, if you can see it, look at that pyramid. That's the view plane. Now look at how big it is. I mean, look, it goes way out past the scene. But okay, this top view, that's what I'm talking about. Okay. So yeah, that's what we're looking at in this crudely drawn diagram that I've got sitting here. So back to this object, right? This is maybe, I don't know, a quarter of the way through the scene. So anything that's sitting right up here is going to have a value of 0. Anything over here is going to have a value of 1. So this is going to have a value of something like 0.25 for that pixel. So say that's that pixel right there. Now if we do another one and we go past the crate to the wall, say it's this point, well, it's actually probably up here, but whatever, just say that's that point. This is probably 0. I don't know, what do you think, 0.4, something like that would be this point. Okay, as the renderer is drawing more objects, so say another object gets drawn in here, it checks that object against the depth buffer, and it says, oh, this point right here we can't see, so I could throw that pixel away because it's already being covered up by something in front of it. But then if there's an object here, it looks at that pixels on that object and says, oh, it's behind this crate, but it's in front of this one, so it would adjust some of the depth buffer that you could see in here, but other pixels it would throw away. Okay, that's how the depth buffer works. So at the end of the rendering process, you have a buffer, this buffer, which kind of shows you in a two-dimensional way the depth of the scene that you're looking at each pixel, if that makes sense. Okay, that we can use to our advantage, right? Now, I need to take a little bit of a sidebar here, guys. Oh, I'm running out of page. Here, let's grab a new page. Okay. I need to talk for just a minute about rendering modes, because this will have an effect on us as far as the depth buffer goes. There are basically two rendering modes. There's forward rendering, Let's make this A. And there's deferred rendering. Okay, in forward rendering, objects are pre-sorted. Oh boy, I can spell sometimes. My handwriting is getting terrible, I can already see that. Are pre-sorted. Back to front. This happens before anything is rendered. And what that means is, if the objects are already sorted, this doesn't need to use a depth buffer. So there's no depth buffer needed. Okay, this is kind of a sidebar, guys. This pre-sorting, this generally works pretty good unless your objects are kind of entangled around each other. So if I have like a box, if you're looking at an overhead view of a box, and I have some sort of object that sits like this around that box, like a wall, or this is, whoops, whatever. Okay, this wall right here is both in front of and behind this box. So how do you sort those objects? That was a common problem with forward rendering. There's ways to fix it, but we don't have to worry about it. I need to get a bigger eraser. Okay. In deferred rendering, objects are rendered as they come to the video card, one at a time. Okay. There's no sorting. And in fact, nothing is rendered at all. They just go into a series of buffers. They're kind of, I need a better word than rendered. They're rendered into buffers. One of which is the depth buffer. So this one already has a depth buffer. So what does that mean for us? Well, if you're in this mode right here, a depth buffer already exists, okay? Because Unity needs it to draw the scene. So we can just grab the depth buffer. But if you're in this mode, there is no depth buffer. You have to actually tell Unity to make one. And this is a performance hit. Okay, this was a slowdown. This was a, yeah. Just leave it at that. Now, by default, guys, we're in this mode. We're in deferred rendering, so we should have a depth buffer. Kind of as another sidebar about deferred rendering. It has a lot of advantages over forward rendering. One thing it cannot do very well is semi-transparent objects. And you can understand why. If I have a depth buffer, right, and I have an object in a scene like right here, and this object is at the pixel's at 0.4, and then I have like this stained glass window right here that's at 0.2. I've actually got 2 points in here, right? I've got the stained glass window depth, which is at 0.2, but I need to see behind that to get this other pixel. Well, you can't, you can't put 2 points here. This is a single point buffer. There's no way to put another point. It's either one or the other. So deferred rendering has trouble with semi-transparent objects. Transparent objects is no problem because you just don't draw them, and of course opaque objects are no problem. But when it comes to semi-transparent objects, then there's an issue with that. The way the engine handles that is it draws everything that's opaque, and then for anything that's semi-transparent, it drops back into a forward rendering mode and draws those as forward rendered objects. kind of back to front. Anyway, that gets off topic. What I'm really after here, guys, is to let you know that we are, by default, we are in deferred rendering. However, it is possible for the engine to drop back into forward rendering mode. In some video cards which don't support deferred rendering, those would be old cards at this point, I think. But still, I mean, I think people use them. So if the card doesn't support deferred rendering, the engine will drop back into forward rendering mode, and then you've got to get a depth buffer, which is going to cause a slowdown. Okay, it's going to make, because this is an extra step that the card has to do that it doesn't have to do with deferred rendering. Okay, well, I mean, it does have to do it in deferred rendering, but it does it automatically anyway. It's not an extra step. It's a normal step of the process. So that's just something to be aware of. Okay. So we know this depth buffer exists one way or the other. We need to capture the depth buffer. Now think about this for a second, guys. The depth buffer is created during the rendering process. This is a GPU function. It has nothing to do with the CPU. Okay? The CPU, which is to say scripts, cannot access the depth buffer. Okay, because it's being handled by the GPU. Okay, the GPU doesn't send the depth buffer back over to the CPU. So how do we capture the depth buffer? The only way to capture the depth buffer is to use a fragment shader. Now, you guys remember, I hope, when I talked about materials, that a material is one or more textures plus a couple of shaders, and one of those shaders is the fragment shader. This is also known as the pixel shader, by the way. The responsibility of the fragment shader is to figure out what color to draw on a particular point on the screen. Okay, basically that's its job. The fragment shader is the one that deals with the depth buffer. So you can take that depth buffer and transfer it to a rendering texture. Now it's a buffer, right? It's really just a two-dimensional array. But the only thing that fragment shaders really understand as far as output goes is textures. Okay, they can't really output a two-dimensional array. So this is going to be, I believe, a red, green, blue texture. It might have an alpha channel in there. I'm not really positive. Really, it's just one point, right? So it actually gets stored in the red channel. The depth gets stored in the red channel. You can actually store other stuff in these other channels. You can put normals in here, but we don't necessarily need to talk about that. This is going to be your depth. Okay. Once you've got it into a render texture, you can send that render texture over to the CPU. You can't send the depth buffer over to the CPU, unfortunately, but you can send a render texture over to the CPU. And this is a bit of a performance hit. Because you're copying the depth buffer over to a texture, and you're sending the texture across the bus over to the CPU. But that's okay. We may or may not, guys, be doing this via replacement shaders. I'm still looking into this. I'm not positive about what I want to do here yet. If it's necessary, I'll talk about that when we get to it. Okay. So from there, we can access the render texture from script. Okay. So I should say this is going to require us to write a shader. We're going to have to write a shader. And this is not something we've done before in this series, but you know, don't let it freak you out. It's not that hard. It's another language. It's not C. It's not C++ or C#. It's a custom language actually for Unity, which I know a little bit of. I'm not a super expert on it, but I know enough to get by. So okay. Okay. So let's talk about what we've got here. We've got this. Essentially, we've got this two-dimensional way. What we're actually going to end up with is a texture, but we can read the red channel of that texture to get the number that we're after, right? But let's think about this for a second. We have our map, right? So I'm going to draw this kind of big. We have our camera. It's looking out into the world at some particular angle, right? Now we've got this depth buffer. Now, if you look at the depth buffer, this guy right here, if you look at a top view of the depth buffer, so this is the depth buffer, top view, right? And I extend this, say this is 0 and this is 1, so you've got some set of values in here like this, right? That kind of look like that. Or whatever they happen to look like, right? So there's some depth, like that's that depth and that's that depth. Okay. But it's not that. Think about it. This point right here, say, is this point. Okay. But this point right here is also this point. And this might have a different value. Like at different elevations, you might have different numbers. Like, so say there's a different elevation that looks like that, right? Or another elevation that's, you know, way out here. So for any given row of values, what do we take? There might be a whole bunch of different values in here, and we just want one of them. Because we need to decide where in this thing we want to cut off that point, right? Maybe it looks like this, after you look at the depths. So which point is what I'm after, or is what I'm trying to get at here? Which point in a given row do we use? Which brings us to the subject of our 14th point. We're going to scan, sorry if that was confusing, guys. I'm not talking about rows here, I'm talking about columns. We're going to scan each column from top to bottom. On our texture. We are going to take the highest value. In that column. Okay, so whatever point is furthest out, that's the point we're going to use. Okay. So what that means is if you're looking at a scene, like say, if there's a scene that you're looking at, and there's like a wall, like a partial wall here. So this is closer to you, and this is further away, and there's like a, you know, something back here, like a doorway. And I'm looking at this point. Okay. You'll scan through all this, and you'll find the furthest point in that row, or sorry, in that column. And it's not going to be here, right? These are closer. And it's probably not going to be here because these are closer. It's going to be something behind this, or through this doorway. Okay, assuming this doorway is open and you can see behind there. So that's what we're going to use for our point for that column, is the furthest point that you can see. Which makes sense if you're thinking about an overhead map. You want to use the furthest point that you can see in that column. Okay, so that gets us to, so whereas before we had whatever this was, 1080 by 768 or whatever it was, I forget. We had this huge array. Now we just got, we've reduced that to 1080 points. Okay. All right, we're getting close, guys. So for each point, we're going to convert that to a world point. Right, so what you have, guys, is you have a camera point here, which is an XYZ. And then you've got some point out here, which is a depth buffer point, which is a number from 0 to 1. Okay, say 0.4, or whatever it happens to be. So you're going to take this, you're also going to take the rotation of the camera, and you're going to take this, and you're going to determine where in the world this point is. Okay. From there, you're then going to convert that to a map point. Again, via the world markers. And this part is simple. This part is a little more difficult. And there's some math in here, right? There's more math in here, but this is easy math. Okay. Okay, so we're getting closer here, guys. We actually are getting close. Now, all we have to do, once we have a camera point in map coordinates, and we have a I don't know, what do we call this, a depth point, also in map coordinates. All we have to do, we got those 2 points. So point A, so here's a map, right? So here's your camera point, and here's your depth point. All you got to do is take all the points on that, the alpha cover, change all alpha, so it's alpha, red, green, blue. You change this point, change all the alphas to 0 between those 2 points. Oh, my handwriting is getting terrible. Okay, and there's various ways to do this. We can use anti-aliasing here. To smooth out that point so it's not so jagged. Another thing we might want to think about doing, guys, if you remember, if we look back at where's it at? Unity. Look at how far this thing is. Okay, that's way too far. So we might want to we might want to cap the distance to between 0 and 0.3 or something like that. And what you might even want to do, if you wanted to be fancy, is from 0 to 0.3 alphas equals 0. From maybe 0.3 to 0.4, these are in distances. Okay, this is the distance points. You set the alphas equal to 0 to 1. So there's a gradient between 0.3 to 0.4 for the alphas to go to 0 to 1. And what that does is the further the stuff far away kind of starts to fade out because you're not so sure what's out that way. Maybe it's a little too dark to see. It's far away, so you kind of draw a partial map of that area. So you might want to do something like that. We could try that out and see what it looks like. So yeah, that's the basic design, guys. It is a complex system, but on the other hand, the whole thing really isn't that tough from a system perspective. From some of the coding might be a little tricky, getting Unity to do what we want, especially grabbing that depth buffer. I expect Unity to give us a lot of grief about that, but I think it's possible. Now, I should say I'm not so sure about this right here as far as performance. That's the big question mark here, guys. I've never coded this before, so what we're talking about is taking 1,080 points and scanning them, 1,080 columns, and scanning them to find a point that we want to use, and then converting that, and then drawing a line. So every single frame we're drawing 1,080 little, basically, lines on the map, right? I don't know how fast that's going to be. We'll have to play around with it and see kind of what it looks like, how well it does, that kind of thing. We may have to take some steps to optimize it after we're done. We might not get this will give us picture perfect mapping. We might have to sacrifice some of that to get reasonable performance. We'll just have to see. I'm not really sure how this will work out, so we'll find out. We'll find out together. I hope it works, because I don't really have any other great ideas. I have a couple of other ideas on how to do this, but they all have issues. So this is the best one I could come up with. So we'll see how it works out. Alright, guys, so in the next video we will take care of that lighting issue, and we will get started on this new system. So I will see you guys then. Thanks a lot.